our first section that we're going to go ahead and cover is going to be section 12.1. And that one's going to be over 3D coordinate systems. So essentially, normally in pretty much all of our math we've done up to this point, we have been in 2D where we have X and Y, like where we just have an X and Y axis and X and Y coordinates. But of course, when we're in 3D, we know our main difference is that we now have a Z axis to worry about. So we also know that instead of having quadrants, since we have that new dimension, we also have to deal with octants instead. And usually if they're going to ask you to like label an octant, they're mainly just going to be concerned with octant 1, which is going to be whenever you have a positive x, positive y, and positive z. They usually don't get as picky with this in 2414. Now, if you take 2415 or 2451 at some point, then they will probably be a bit more picky with this. But for the purposes of this exam, they're probably not going to be that picky. So now that we actually have these, another big difference between 2D and 3D is the inclusion of, the inclusion of coordinate planes. And whenever we think of coordinate planes, we have three main ones that we think of. We have XY, XZ, and YZ. Your textbook actually has a really good example. They kind of think of these as being kind of like the walls and floor when you're thinking of a room. So for example, if we have our Z-axis going up this way, we have our X-axis going up this way, and our Y-axis going this way, our XZ plane is going to cover all of this. We can think of that as being that wall. Our YZ plane is going to quote unquote be the other wall. Give me just a second, my pen's acting up right now. There we go. We have our YZ plane over here, and like our quote unquote floor would be our XY plane. Now, these can kind of shift around depending on how you want to play with it, but once again, for the purposes of this course, I would just kind of think of it in that way. And now that brings us to a next big skill that we need to learn for this chapter, which is going to be graphing. So, plotting points is going to be a pretty big part of the section. So what we're going to go ahead and do is, let's go ahead and do an example. So for example, we want to go ahead and plot the point -2, 3, and 1. So what we're going to do when we do this is first you're going to go ahead First, we need to go ahead and draw our X, Y, and Z plane, or like our graph. So we're going to typically have our Z is going to go up and down. Our X is going to kind of come, quote unquote, like out of the page. I mean, that's a Z. And then our Y is going to be going along, is going to be going left to right. So typically with this, it's kind of like whenever we first started learning how to graph 2D coordinates, we kind of think of this as one piece at a time. So let's kind of go ahead, since we know we have a negative x, let's kind of go ahead and kind of draw that negative x-axis in there. So we're going to go ahead and just move 2 units, 1, 2, along in your x direction, 3 units along your y, so we're going to go 1, 2, 3, and then just go 1 up. So that point right here would be your final point. So now that we've kind of covered graphing, we can now cover projection, since that's another main skill that we're going to talk about. So projections. This is essentially when we are projecting a point, that essentially means we are kind of, quote unquote, kind of moving the point to a line or plane. So if you want to think about it graphically, you can think about it as if your origin and your point are two opposite vertices on a cube. And then you can kind of move that point along the edges of that cube to get where you need to be. But algebraically, it's actually a lot quicker. Like, it's actually pretty quick once you kind of understand the concept. When we do it algebraically, we are essentially replacing a coordinate with a number. So it kind of depends on what exactly you're projecting. Usually when we're talking about projecting, we're usually talking about doing it onto a coordinate plane. So for example, if we're going to go ahead and, so for example, let's say we want to plot that, we want to move that point that we just had. We want to project that point -2, 3, 1 on each coordinate plane. So first thing we can go ahead, let's go ahead and label each of our coordinate planes. So xy, xz, and yz. So if we are on the xy plane, what does that mean for z? So someone can just kind of type that in the chat. Yes, z is going to equal 0 if we're going to be on our xy plane. So therefore, what we're going to do is we're going to keep our x and y coordinates the same. So we're going to keep our -2 and our -3, but we're going to replace that z with a 0. Or if we think about it back up here to this graph, we're essentially just kind of moving that point kind of back down onto our xy plane. Yeah, we're going to move it right here. And it's a similar concept for the 3 coordinate planes. If we have our xz plane, then y must be 0, so we keep our initial, we keep our other 2 coordinates though. And yz, it's the same thing, but instead x is 0, and we keep y and z. And we can even go ahead and project onto a line. So for example, let's say we want to project that point onto, let's say, the x-axis. We know that that is going to be when our y and z are both 0. So therefore, that projection would be -2, 0, 0. So the next topic we need to talk about is surfaces. So for surfaces, we need to be able to know how to draw and describe surfaces. So my advice for this, when doing surfaces, is kind of draw a 2D picture for each coordinate plane. and then and then take all those and kind of convert that to a 3D picture. And now when we have to actually think about describing, the big points that you want to include are some good details to include are maybe, is it parallel or perpendicular to, let's say, to either like a coordinate plane or to an axis, or just some sort of reference for the direction. What is the shape? So in this course, the main shapes that you're probably going to give you are either going to be a plane. So that's just going to be like a straight sheet, no curves, pretty simple. A cylinder, which essentially that's just going to be round going in a certain direction, or a sphere. So those are your main ones to know. And then maybe add some sort, maybe describe a direction. And another thing you can add is maybe put like a reference point. So for example, like if you have like a plane and it's kind of hard to describe it, you could say like, or if you're trying to figure out a way how to be more specific, you could be like, oh, this plane is parallel to the XZ plane and it goes through the point 2, 3, 5. And that should give you a good amount of instructions for that. And now that we're talking about surfaces, another big thing to keep in mind is going to be surfaces versus solids. And the big difference to those is that surfaces have no thickness, and they're given you in terms of, and they're described in terms of an equation, like you have an equal sign. Solids are fully or partially filled, and they are described in an equation as being, or they are described as an inequality. So for example, if we wanted to go ahead, so let's do an example. We want to go ahead and graph and describe where'd it go? The this graph, x squared plus z squared is less than or equal to 9. So if we wanted to go ahead and graph this, we can go ahead and start off by doing everything in 2D. So we know that if we have an xy plane, we have no description for y, so we can't really like graph this because it could just, we only know that x squared has to be in between, that x squared is less than or equal to 9, so it has to be in between 3 and -3. But it can kind of cover everything like this. And it's a similar idea if we have our y and z plane. Except this, our z squared is going to be less than or equal to 9, but we have no limit for y. So we can go ahead and just say it's something like this. And then lastly, if we look at our xz plane, we can see that this, if we have x squared plus z squared is less than or equal to 9, we know that's going to be a circle with a radius of 3, and it's going to be filled. So if we go ahead and combine all of these, we can draw our XYZ graph. So Z, X, Y. We know we're going to have a circle on our XZ that's going to have a radius of 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. So we're going to kind of draw our little circle in like this. And then we know that it's going to keep traveling along our y direction. And then, of course, it'd be solid, so we're going to fill it in and then say that if we were describing it, we have a solid cylinder with a max radius of 3, centered around the y-axis. So that kind of gives us a description, it shows us the shape, tells us how big it is, and it gives us a location. And when you say centered around y-axis, that implies that it's also traveling along the y-axis because it's a cylinder. So quickly, because that way we have time to get through everything. We also have distances, our distance formula. Is going to be our distance between 2 points, so 0.1, 0.2. When we're dealing in 3D, is going to be very similar to our 2D. And that's going to be x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So very similar to our 2D. We're just throwing in that z. And another important formula to remember is going to be that if we have a sphere with a center at HKL and a radius of r, then as an equation, it would be represented as x minus h squared plus y minus k squared plus z minus l squared equals r squared. If we have time, I may come back to do an example, but let's kind of go ahead. Does anyone have any questions for section 12.1? All right. If no one has any questions, I'll go ahead and move on to 12.2. So section 12.2 is going to be vectors. So of course we know that vectors, they can be shown visually and graphically. Visually and algebraically. So visually, we know it's just going to be a graph where you have your ends, or what they call like your tip to your tail, and your tail's and you have your initial and your terminal point. Or you can do components in the form x, y, and if you're in 3D, z. Or you can do xi plus yj plus zk. So some important things to know, to remember for this is going to be, so just some mathematical operations is going to be vector addition. So graphically, if we're, so remember graphically, we're going to just kind of go, if we have A is this and B is this, and we're wanting A plus B, we're going to go draw A and then connect B to the terminal point of A, and then connect the initial point of A to the terminal point of B, and that will be A plus B. Or if you're in components, you can just add your components together. So add all of your x's together, and that's your new one. Add your y's, that's your new one. Add your z's, that's your new one. Scalar multiplication. So if we're thinking about that in terms scalar multiplication, if we're thinking about this in terms of it being graphically, remember that's going to go ahead and essentially change how long it is. It's going to change the length, but the direction will either be the same or if it's negative. So if we have A, then this would be 2A. Or if we're going, or if we're doing negative scalar multiplication, of course we just flip it 180 degrees. And once again, if you're working with components, you just distribute that scalar across all of your components. Subtraction. Once again, if you're working with components, you just subtract your components as normal. If they're asking you to maybe draw something, what you would do is, if you have vector A is this and B is this, what you would do is you would draw vector A as normal, but B you would draw going in the exact opposite direction. So we're going to go up instead of down, and then that resultant vector is going to be your A minus B. And of course, the last things for section 12.2 to kind of think about are going to be magnitude. Magnitude is going to be very similar to our 3D and 2D coordinates. If we are in 2D, the magnitude of vector A is going to essentially be, if our vector is in the form A1, A2, it's going to be the square root of A1 squared plus A2 squared. Or if we're in 3D, so where we have A1, A2, A3, our magnitude is going to be A1 squared plus A2 squared plus A3 squared. Does anyone have any questions over this section? All right, so I will go ahead and move on to chapter 7, since I know this is probably the stuff that you're more interested in seeing anyway. So chapter 7 is going to, of course, be our chapter on integration. So our first section that we have is going to be chapter 7.1, section 7.1, which is going to be integration by parts. So, of course, if we remember, when we do integration by parts, that's essentially saying that if we have the integral of some function u times some dv, then that is going to be the equivalent of u times v minus the integral of v du. So a big thing to remember when we're doing integration by parts is going to kind of be the priority list for how we determine what u is. So our way that we can determine which one to assign to u is going to be the acronym LIATE. So we have LIATE where the L stands for is going to be a logarithmic function, and I is going to be inverse trig. Our A is going to be algebra, is going to be an algebraic function. Our T is going to be a normal trig, and our E is going to be an exponential. And just one important note, because this may come up, is that if you just have a plain dx or like a 1 dx, that can count as an algebraic. That can count as an algebraic, but usually if you have that, that's going to have to be your dv. But that's where it would fall in case like you ever need to know. All right, let me go ahead. I think we have a question here. Yeah, so that's a good question. We had someone say that they learned a different one, LIPET, so log, inverse trig, polynomial, exponential, and trig. So they're asking if exponential and trig have the same level. Pretty much yes, because for both of those, you're going to kind of get stuck going in like a loop. If you try to assign that one for you, you're going to kind of keep getting stuck in a loop because every time you derive a trig function, you're just going to keep getting more and more trig functions. You're going to eventually get in a loop. Same thing with exponentials. So yeah, I would say those are approximately the same priority. So I'm going to go ahead and do a really quick example for integration by parts. So for this one, we are going to have the function ln of x over x squared dx. So does someone want to, you can either use the microphone or just type it in the chat. What would you assign to be our u? Yes, our u is going to be natural log of x. So therefore, our dv is going to have to be 1 over x squared dx. So if our u is natural log of x, our du is going to be 1 over x dx. And if we integrate our dv, so that's our integration of x to the negative 2, that will get us negative 1 over x. So let's go ahead and set it up. We have our uv, so that's going to be negative x times negative 1 over x, so negative ln of x over x, minus our integral of our v du, so we have 1 over x times negative 1 over x, so negative 1 over x squared dx. I'm just going to go ahead and pull out, take care of that double negative. So we're going to integrate x to the negative 2 again, which we already said was negative 1 over x. So we're going to be getting negative natural log of x over x minus 1 over x plus C. Does anyone have any questions about integration by parts? All right, so let's go ahead and move on to section 7.2. And this one's going to be over trig integrals. So for trig integrals, this one's kind of a formula-heavy section. So your important formulas to know are going to be your Pythagorean identities, and a good tip is that most people have no problem memorizing this one, sine plus cosine. You can actually play with this equation and derive the other two. So if you divide both sides of this equation by cosine squared, that will get you your tangent and secant identity. If you divide both sides by sine squared, that will get you your cosecant cotangent identity. So that's just a good way to kind of help memorize that, or like if you forget it, then that's the way how you can go back and solve for it. You need to remember your power reduction identities. Which is essentially going to be if you have like a sine squared or a cosine squared, that's how you're able to get rid of that if you can't like do a u sub. So you can bring that down to like a power of 1. That way you can go ahead and integrate. There's going to be a couple other miscellaneous trig identities. And those are essentially going to mostly be like your double and half angle. And I know that is in the handout that's in the e-learning under formulas to know. They'll have the ones that you need to know for the exam. And the last ones that you kind of need to know for this one are going to be just the new integrals, which are going to be your integral for secant, integral for tangent, integral for cosecant, and integral for cotangent. And once again, those are all listed. Everything on here is listed in that handout for formulas to know. So now that we know that's kind of like things to kind of keep in the back of your mind for the exam, let's go over how to actually strategize for this. So when we do this, there's a few main strategies based on like what we actually have in our integral. So if we have an integral involving sine to some power, we're just going to say m times cosine to some power n, there's a couple different ways that we can work with this one. So if the power of cosine is odd, we are going to save one piece of the cosine of x, convert your cosine to sine, convert every other instance of cosine of x to sine of x using your Pythagorean, and then you can do a u sub, or u is sine of x. Similarly, if sine is odd, you'll do the same thing. You're just going to save one sign, convert the rest of those to cosine of x, and then do a u sub for cosine of x. Now, the issue is if both of them are odd, you can just pick whichever one you want to do. You'll get the same thing. The issue comes is if both of them are even. And in that case, you're going to have to use those power reduction formulas in order to break that down into something that you can actually integrate. So I'm going to do a quick example for like how to work with sine and cosine. So if, for example, we are integrating sine squared of x times cosine to the fifth. What we're going to do is we're going to go ahead and take out one cosine. So we're going to go ahead and say that we have sine squared of x cosine to the fourth of x times cosine of x. We're then going to go ahead and convert that cosine to the fourth in terms of sine. So where we're going to get sine squared of x. I'm going to go ahead and skip this step and say that we're going to have, since we know that cosine squared is equal to 1 minus sine squared of x, and that's squared since you're going to the fourth, cosine of x dx, expand out that 1 minus sine squared. So we're going to get 1 minus 2 sine squared of x plus sine to the fourth of x cosine of x dx. So then we're going to go ahead, distribute that sine squared. We're going to get sine squared of x minus 2 sine to the fourth of x plus sine to the sixth of x, all times cosine of x. And now we can just do a basic u sub to where we can say that u is equal to sine of x, and we know that du is cosine of x. So therefore, we're going to get u squared minus 2u to the fourth plus u to the sixth du. If we integrate, we're going to get 1/3 u to the third minus 2/5 u to the fifth plus 1/7 u to the seventh plus c. And then just go ahead and put your sign back in, and we're done. So your next group of problems that you could see from this section are going to be if you're dealing with tangent and secant together. So if the power of secant is even, what we can do is we can go ahead and save one little secant squared. And in a similar way we've been doing, convert the rest of them to tangent and do a u sub where u is equal to tangent of x. If our tangent is odd, this is where it slightly differs from the last one, we're going to save a secant tangent, convert to secant, and then u is equal to secant of x. Now, the one main difference between this set and the sine and cosine is that while there is an easy way out by doing power reduction in the other one, we don't necessarily have that when we're working with this. So if you get stuck to where, let's say you have an odd secant and an even tangent, you may have to kind of play around with it some. If you get stuck, some other ways you could do is try doing integration by parts. You can go ahead and try converting to sine and cosine. Or you just kind of have to maybe just play around with it some more and see if there's another alternative option in order to kind of get you out of that. And then our last section group that you could potentially see, probably not that often, but they could come up on the test, is going to be when you have cotangent and cosecant. So it's very, very similar to the last one. So if cosecant is even, save a cosecant square, and then convert and do convert to cotangent and do a u sub for cotangent. If cotangent is odd, save a cosecant cotangent, convert to cosecant, and once again do a u sub. Now, once again with the last one, if you get stuck, once again try integration by parts, try converting to sine and cosine. But the big thing is if you run into this, is make sure to check your signs, because those deal with like a lot of negatives when you start messing with cotangent and cosecant. So yeah, just make sure you really pay attention to your signs on those. Does anyone have any questions about this section? All right. So now we're going to go ahead and move on to the next section. I think this is probably the hardest one. We're going to do is trig substitution. Trig sub is just hard. Like really, I feel like trig sub is really hard just because there's it's a lot of algebra, a lot of trig identities, a lot of conversion. So this is when we're going to have to really kind of stay organized when you're trying to work through these. So of course, your important formulas are going to be, for sure, be your Pythagorean identities, as well as a lot of those same trig identities we talked about in the previous section. So let's go ahead and just do a quick review about how we implement this. So we're going to have our format. our substitution, and the identity it's based off of. All right, so if we are given the format where we have some constant a squared minus some x squared, our substitution is going to be x is equal to a sine of theta, and we implement that because 1 minus sine squared of theta is equal to cosine squared of theta. If we are given a squared plus x squared, we can do x is equal to a times tangent of theta, and that is because 1 plus tangent of theta, or tangent squared, is secant squared. And our last format, main format that we'll be looking at is x squared minus a squared. So in here we can say that x is equal to a times secant of theta. And we can say that secant squared of theta minus 1 is equal to tangent squared. So let's go into how to actually, now that we have this info down, let's kind of go in how to actually solve this. So our first step that we need to go ahead and do if we're doing a trig sub is apply our substitution. So we pick one of those three, so we look at our format, we pick one of those three substitutions, and then just plug everything in. Plug in thetas for all of our x's. Our second step that I would do is go ahead and try simplifying what you have in your function, because you can sometimes get a bunch of different trig identities. If we can get a bunch of different trig pieces, if we can just go ahead, slash some stuff out, it's going to make our lives way easier. Our step 3 is going to be to go ahead and actually solve our integral. And I usually like to go ahead and, of course, I'm one of those people where I prefer to go ahead, solve, and not worry about like changing my bounds until I don't like some people find that really helpful, changing their bounds along with the substitutions. But if you're doing a trig step, I would definitely wait until you kind of get back to where you start. So solve your integral. Step 4 is going to be to build your right triangle based on your initial substitution. And our last step is going to be to convert back to x. So I'm going to go ahead and do an example for this one. So for this example, we are going to do the integral of dx over the cube root, or let me just, x squared minus 1 to the 3/2. So if someone wants to turn on their mic or type in the chat, what should we use for our substitution? Like which idea, like x should be equal to what? Yes, x is equal to secant theta. So we can say that x is equal to secant of theta, and therefore we also know that dx has to be equal to secant theta tangent theta d theta. So let's go. So our first step, like we said, is going to be to go ahead and apply our substitution. So convert everything into terms of theta. So we're going to have our dx, like we said, now goes to secant tangent d theta. And then, of course, we're going to plug in our secant squared and for our x squared. So we don't quite have anything we can get rid of yet, but we can go ahead and say that this secant squared of theta minus 1 is now going to go down to tangent squared. So we now have secant theta tangent theta d theta over tangent squared to the 3/2. This tangent squared and then that little like half down here are going to cancel. So we're just going to be left with secant theta tangent theta d theta over tangent cubed. So does anyone see anything that we can go ahead and try to simplify out? Like we can go, so yep, we can go ahead and cancel out those, that tangent. So we can get tangent, and then that becomes a tangent squared. So now the issue is, so now we have secant theta over tangent of theta, and we can also say that that could be equal to secant times cotangent squared. Now, for this one, this doesn't quite match any of our identities that we had in the previous, in 7.2, because we'd either need a secant tangent or a cosecant cotangent. But we can still actually go ahead and play with this and see if we can figure out anything. Yes, that was exactly what I was about to say. Someone said we can cancel out our cosines. So yes, we can go ahead and turn everything to sine and cosine. 1 over cosine of theta times cosine squared of theta over sine squared. When in doubt, always convert to cosine and sine. So this is gone, and this is gone. So we now have cosine over sine squared. And then now what we can do is we can actually go ahead and break this down and say that we have cosine of theta over sine of theta times 1 over sine of theta d theta. We know that cosine over sine is going to go down to cotangent. And we know that 1 over sine is going to go to cosecant. So what is this going to give us? All right, so this is actually on our formulas to know sheet. So this is actually going to get us back to negative. This is going to be equal to negative cosecant of theta plus c. So we finish. So we have gotten through our Yes, you could also do a u sub right there as well. You can do a u sub and let u is equal to sine of theta and du is cosine d theta. If you don't remember that formula, it'll get you the same thing. It's one less substitute. Since we're already kind of doing it's just one less substitution to have to deal with. But if you want to solve it with the u sub right there, you're perfectly good to do that. Yeah, pro tip, a lot of those trig identities, if you want to go ahead and like play with those a little bit, like on the formula snow, some of them you can play with and find alternative ways to solve for them if you don't remember them. Like I know another good way to do that one is like with the inverse trig. Usually with those you can solve for those like using a trig sub or things like that. So yeah, if you have time or when you're studying and you want to play with some of those formulas and see if there's another way, you're good to go. So our next step would be, of course, to draw our right triangle. So I'm going to go ahead and switch colors. We, of course, said that x is equal to secant of theta. And we can say that that is x over 1. And we know that secant of theta is hypotenuse over adjacent. So we draw our right triangle, theta, hypotenuse is x, adjacent is 1, so therefore our opposite is going to be square root of x squared minus 1. And you should know if you're on the right track because when you're building your right triangle, you should always end up with that initial term that you had. So we know we have cosecant of theta. So cosecant is, since that is the opposite of sine, is going to be hypotenuse over opposite. So therefore we know that that is going to, so we know cosecant of theta is going to be x over square root of x squared minus 1. So just throw a negative in front of that. And we have square root of x squared minus 1 plus c. And trig sub, it doesn't necessarily have to be just in like exactly those formats. There's a couple other good, there's a couple other uses and just some other tips that I have for this. So it does not have to necessarily be under a radical. It usually helps because it helps cancel stuff out, but it doesn't have to be under a radical. Like if you want to try solving like the inverse tangent, like you can go ahead and solve the inverse tangent integral by Yeah, you can solve the inverse tangent integral by doing a trig sub, and because that one's not under a radical, but you can use that process to get you the answer. So it doesn't have to be under a radical. And another good thing that you can use, like another kind of idea that we can use is completing the square. You may get a couple questions like this, and I'll actually do an example for that one because I know those can be kind of like, those can sometimes be a little weird. Usually if you're like completing a square, sometimes you may have better luck doing a U sub or some other, or maybe like a integration by parts, but you may have a couple instances where you can do a trig sub. So an example for this would be, let's say we have the integral of dx over the square root of x squared plus 2x plus 5. So we can't do a u sub. There's not really much we can do with this just yet. So what we can do instead is we can go ahead and take this radical and try seeing if we can play with this to get us into a form where we can do a trig sub. So we can do this by completing the square. So we know we have an x squared and a 2x. And what we can do is we can say we have a plus 5. We can group that x squared plus 2x and complete the square and add a plus 1. And we just have to remember to take off another 1 right here. So therefore, we would get x squared plus 2x plus 1 is the same thing as x plus 1 squared plus 4. All right, so we now have dx over the square root of x squared, of x plus 1 squared plus 4. And then from here, what we can do is we can say that, I'm going to go ahead and switch colors, and say that we can say that u is equal to x plus 1 and du is equal to dx. And that will get us the new integral of du over the square root of u squared plus 4. And we can now that puts us in the exact format for a tangent trig sub, so we can do another substitution to say that u is equal to 2 tangent of theta and du is equal to 2 secant squared of theta d theta. Plug everything in to get us 2 secant squared of theta d theta over 4 tangent squared of theta plus 4. And then we know that 4 tangent squared of theta plus 4 is going to simplify out to 2 secant squared. So we're going to get 2 secant squared of theta d theta over 2 secant of theta. These are going to cancel out. And we know that the integral for the secant of theta is just going to be the natural log of the absolute value of secant plus tangent. So our last step would be now to go ahead, draw our right triangle. We said earlier that u is equal to 2 tangent of theta. Therefore, u over 2 is tangent of theta, which we know is equal to opposite over adjacent. So we have our u, our 2, and our square root of u squared plus 4. So therefore, we are going to get natural log. Secant of theta is going to be hypotenuse over adjacent. So square root of u squared plus 4 over 2 plus tangent, which we already said was u over 2. And then lastly, we can just go back and convert back to our initial u sub. So we're going to get square root x squared plus 2x plus 5 when we kind of redistribute everything over 2 plus x plus 1 over 2. So that is an example of how you can do a complete the square with trig sub. As you can see, they can get kind of long and when you start doing multiple substitutions, they can get a little messy. So if you do have that situation, I would personally recommend, like I said, either seeing if you can do a u sub, see if there's a way you can maybe do some sort of rationalization, but if worse comes to worse, this is always an option. So does anyone have any questions over trig sub? All right, so our next section that we need to cover for this exam is going to be section 7.4. Which is partial fractions. So partial fractions, they are going to be used with rational functions. And by that we mean that, like, if we have a function f of x, which could be broken down into saying that we have a function p divided by function q. And essentially these are used to go ahead and break down f of x into something easier to integrate. And this is usually, and when we do this, we usually end up using a natural log or a power rule. You may have a few exceptions here and there, but these are usually the main rules you'll use whenever you actually have to integrate. Now, one big thing to remember is if you're going to do partial fractions, if the degree of p, or your numerator, is greater than or equal to the degree in your denominator, you have to, you must perform long division before you start partial fractions. So now that we have that out of the way, let's kind of go over our basic rules when it comes to partial breaking these down. So over here, we're going to say this is the factor in our denominator. And over here, we're going to say like what is going to be the term in our decomposition. So if we have just a normal linear factor, so ax plus b, that is going to turn into, we're going to use some constant a over ax plus b is going to be the term in our decomposition. If we have a linear factor raised to a power, then we have to go ahead and take that into account throughout our decomposition. So what we'll do is we can say that we have a over ax plus b to the n plus b over ax plus b to the n minus 1. And you keep taking it down one power at a time until you get down to just plain ax plus b. If we have a quadratic factor, we have to go ahead and take that quadratic into account. We're now at a higher power, so that would actually break down to ax plus b over ax squared plus bx plus c. And lastly, if we have a quadratic raised to a power, it's the same concept as when we had a linear raised to a power. So now you'll have ax plus b over ax squared plus bx plus c to the n plus cx plus d over ax squared plus bx plus c to the n minus 1 until you get down to just ax squared plus bx plus c in your denominator. And now you can continue this power, like if you have a factor with like a cubic factor that you can't break down or just any bigger power, you can do the same format. You just know that the numerator, when you do your decomposition, is going to have to be one less than the power that you have in the denominator. And if that factor is, raised to another power, you have to take that into account and just do additional ones. But you can do that if you have some cubic factor that you can't get rid of. You typically won't see that often, but you can do that. So I'm going to go ahead and do a quick example showing the full integration, and then I'll do another one we're just going to do the decomposition, but that one's just a little more complicated. So oh wait, you have a question? Let me see. All right, that's good. All right, so partial fractions. Our first example we're going to do is we're going to go ahead and integrate 3x minus 2 over x plus 1 dx. So we can't really do much with this. We're going to have to do a partial fraction decomposition. But we also have to remember, we said earlier that if the degree in the numerator is greater than or equal to the degree in the denominator, we have to long divide. So we're going to have to go ahead and start with that. So we're going to put x plus 1 into 3x minus 2. So x plus 1, so if we have our first term as x and our first term over here is 3x, we're going to multiply this whole term, this x plus 1 times, we need 3 of those. So then we're going to multiply that term times 3 and subtract. So we're essentially going to say 3 times 3x plus 1 is 3x plus 3. So we're going to subtract that from what we have up here. So minus 3x minus 3. Those 3x's are going to cancel out, so we're left with a negative 5. So, and negative 5 will be our remainder. So we now can say that we have the integral of 3 minus 5 over x plus 1. And this one was actually simple enough that we don't even really need to do a full partial fraction, because we can actually just do power rule and log and say that we can do a power rule and get 3x minus 5 natural log of the absolute value of x plus 1 plus c. So yeah, always make sure if you can long divide, do that, because that could save you a lot of work. So now into the actual decomposition. And this one, we're just going to go ahead and solve the decomposition and not actually worry about integration, because like I said, most of these integrals aren't that bad once you can get it broken down. So we have x cubed plus 4x plus 3 over x to the 4th plus 5x squared plus 4. So our first thing we can see, our numerators has a degree of 3, our denominator is at 4, we're good, no need to do any long division. So next thing we need to look at and see if there's a way we can go factor our numerator and our denominator. So our numerator does not appear to have any like easy factors. Now, if we look at our denominator, we can see we have a power of 4, 2, and 0. Going off of that, we can actually play with this a little bit, and we can actually try to FOIL this out. And it does actually FOIL out to x squared plus 4 times x squared plus 1. So if you have something weird where it looks like a normal quadratic, but even if the powers are a little bit different, you can still try to play with it and see if it can factor out to something you can work with. So looking at this, neither x squared plus 4 or x squared plus 1 are going to be able to factor out. So we can say from here that we have ax plus b over x squared plus 4 plus cx plus d over x squared plus 1. So now let's go ahead and put this together. When we do a decomposition, we have to think about this in terms of where do we start? Like how I kind of think of this in kind of almost in terms of a loop. We broke it down. Now what do we need to do to put it back together? So of course we need to go ahead and cross multiply. And we can say that our numerator, x cubed plus 4x plus 3, is equal to everything cross multiplying up here. So it would be ax plus b times x squared plus 1 plus cx plus d times x squared plus 4. Now, if we had like a linear factor, what I would say is we can try to plug and chug numbers just to kind of help eliminate some of these variables, but since none of these have zeros, can actually get to a point where they would equal 0, we can't do that. So instead what we're going to have to do is we're going to have to go ahead and solve a systems of equations. So in order to do that, we need to go ahead and expand all of the expand this whole big equation to get us x cubed plus 4x plus 3 is equal ax times x squared is ax cubed, ax plus 1 is just ax, b times x squared is bx squared, b times 1 is b, cx times x squared is cx cubed, cx times 4 is 4cx, d times x squared is dx squared, plus d times 4 is 4d. So now what we need to do is we need to go ahead and look at each power and see if we can kind of play with this and separate this out by the powers. So we have an x cubed, an x squared, an x, and we have our constant. So if we look at this, on one side of the equation, we know that our coefficient for x cubed is 1. So now we need to see what are all of our terms of x cubed that could get us to that coefficient of 1. So we have an a and we have a c. So we can say that 1 is equal to a plus c. Now we can move on to our x squared. We can see we don't have an x squared on our left side, so that's 0. And on our right side, we have our bx squared and our dx squared. So 0 is equal to b plus d. For our regular x, we can see our coefficient is 4 on the left, and on our right, we have a and 4c. And then for our constant, we have 3 on our left, and on our right, we have b and 4d. So going from here, we need to be able to kind of play with these systems of equations and see what we can try to eliminate. So this one is kind of nice because we have A's and C's grouped together and B's and D's grouped together. So what I would do is we can make some systems of equations based on those. So we can say 1 is equal to A plus C. And the other equation for that system would be 4 is equal to A plus 4C. And then we can set up our second one as being with our B's and D's and say that we have 0 is equal to B plus D, and 3 is equal to B plus 4D. So let's go ahead and start off with the one with our A's and C's. So if we think back to, I know I learned this in Algebra 2 with systems of equations, we can do our elimination technique. So what we can do is we can multiply, we can see A would be easy to eliminate by multiplying the top equation times -1. So negative, negative, negative. Add those equations together and you get 3 is equal negative A plus A, that disappears. Negative C plus 4C is 3C. Therefore, we can say that c is equal to 3. And we also, c is equal to 1, misspoke right there. And we also know that if a plus c is equal to 1, and if c equals 1, then a has to be equal to 0. Now, if we move on to our other system, once again, we can do a pretty easy elimination by multiplying the top equation times -1 to get rid of b. So we're going to have 0, negative b, negative d, add those together. 0 plus 3 is 3. Negative b plus b is 0, and then negative d plus 4d is 3d. So therefore, we know that d is equal to 1. And if we go back to our initial equation, we know that 0 is equal to b plus d, which is 1. Therefore, b is -1. So now what we can do is, now that we have all of our coefficients, we can go ahead, scroll back up, look and see what that was attached to, and then just plug it in, and we'll have our decomposition. So we can now say that we have a is 0, b is -1, so we have -1 over x squared plus 4 plus, we know c is 1, so x, and d is 1 plus 1 over x squared plus 1. So we're not going to bother with integrating that. We're just going to break it down. So that is all I have for, oh yeah, and partial fractions. Just another thing to keep note of is our new formulas from this section. Our new formulas, of course, that to look over are going to be dx over x squared plus 1 is going to be inverse tangent. Dx over the square root of 1 minus x squared is equal to inverse sine. And dx over x square root of x squared minus 1 is inverse secant. And make sure you have your absolute value with your secant. And with all of these, if you're unsure about them, you can always try like a trig sub. You should be able to do a trig sub for all of these and get you the same thing, if like you don't remember it off the top of your head. So does anyone have any questions for partial fractions? All right, so let's go ahead and move on to integration strategies. We're just going to kind of touch on this real quick since this is essentially a review section within a review. So 7.5, integration strategies. This is essentially saying we have all this information. How do we compile it and work with it? How do we just solve integrals in general? Step 1 is going to be simplify your integrands, see if you can get rid of anything. Step 2, look for an obvious solution. So by that, do you have like after you simplify, do you have something that you can just plug in that's a normal rule, or do you have something that's in like an easy use sub? So like if you have like sine of x times cosine of x, you can just do an easy use sub for that. Step 3, If you can't find an obvious solution, use the form to find the solution. So if you have some trig identities, you can do our trig integrals that we did in 7.2, or like a U sub of some sort. B, if you have a rational function, you can go ahead and do partial fractions to break that down. For part C, or like another idea, if you have two or maybe more functions multiplied, you could try integration by parts, and ideally, if you have like an algebraic function, so like a polynomial, and a transcendental function, and that transcendentals are going to be like logs, exponents, and trig. Because those are usually going to be the ones that are going to work out the best. But you can still like play with it and see what you need to do. And our last like main form that we can use is if we have a radical. You can look into doing trig sub, or maybe a U sub in some cases. But usually you can look into doing trig sub. You may have like maybe rationalize it with some sort of U sub, but those are like the main ones. And of course, if you have some sort of like plus or minus x squared plus or minus a squared, that's another sign to look into trig sub. And if that still doesn't work, you can go ahead and just try again. So if that doesn't work, you have a few options. You can try using a different substitution. So like if you tried doing a U sub and it didn't work, maybe try expanding or narrowing that U sub. If you did integration, you could use a different integration by parts. So like if you did integration by parts and that combination of functions didn't work out, maybe try rearranging it and grouping things together a little differently. Part C, or like another one, would be try playing with the integrands and like do different algebraic manipulations with it. So like if you think back to like whenever we did the proof for secant of x, that's a good example of kind of messing with things that you have in the integrand to get you to a form where you can say, oh, I can integrate this now. And speaking of that, what we can do is think back to previous problems. So for example, maybe you may get in a situation and the solution may be to set it equal to itself, like when we solved for the secant integral. And lastly, part E would be to just kind of combine methods. So like as we saw earlier, you may have some situations where you do like a trig sub and a U sub, or you may have to do like partial fractions and trig sub together. So that's just my main thing, just kind of almost make like a mental flow chart of like, okay, here's what I have, here's the format I have. I could have these formulas, I have these strategies. What can I do to go ahead and match those? So Does anyone have any questions before we move on? All right. So our next section that we're going to cover is improper integrals. We're almost done, just 2 more sections. So improper integrals, we mainly have 2 types, or at least that's what it is in the book and what it looked like it was in your notes. I know sometimes they change it on it. They changed it at one point. I don't know why they would redo the classifications, but that's above my pay grade. But for but essentially there's 2 main ways where reasons why it could be improper. So for type 1, we defined it as being like if you have like infinite bounds. And the 3 ways that it could look like are essentially if you are going from some constant a to infinity, or if you're going from negative infinity to some constant b, or if you're going from negative infinity to infinity. Now, here's how we can go ahead and play with this and make it so we can actually integrate this. Because we can't just plug infinity in, since infinity is not an actual number, it's more of a theory and a concept. We can essentially take the limit and use that to approximate. So we can say for the first one, we can take the limit as t approaches infinity and go from a to t. Similarly, if we're going to negative infinity, we can do the same thing. We can just plug in and go to and take the limit as we approach negative infinity. Now, if we have a situation where we have a negative infinity going to infinity, we're going to have to actually break this up, since we can't have 2 limits within the same integral. So what we can do is we can go ahead and just pick any arbitrary point that we want and call that point A. And we can say that we can break that up into 2 integrals and say that we can go from negative infinity to a f of x, and then have another integral going from a to infinity. And then you can just go ahead and use the first 2 examples to break those down. So the other reason why integrals can be improper is if they have a discontinuity within their bounds. So what this can look like is if we have some points, if we know that our function is continuous at A and then has a discontinuity at B, so we have a parentheses at B, and we end up having the integral from A to B, there's a discontinuity at B, so we can't actually solve for our true bounds at B. So what we can do is we can actually say that we can approximate at b by taking the limit as t approaches b from the negative, since that's going to be the side closest to a, of the integral from a to t of f of x. Similarly, if we are discontinuous at a, but we are continuous at b, we can treat this the same way. But instead, we can take the limit as t approaches a from the positive, since that's going to be the side closest to b, of t to b of f of x. And then lastly, we have another interesting case. So let's say we have a is continuous until it hits c. And then it stops being continuous at c. And then, but that's like the only point where it does have a discontinuity within your bounds. So if you have a discontinuity between your a and b, you're going to have to once again break this up into two separate ones. So now that we've kind of shown like how these can be improper, let's also talk about what the limits have to do. So we can say that an improper integral is convergent if the limit exists. However, if the limit does not exist, it is considered to be divergent. And this is typically because the limit goes to infinity. And when we think of this, all limits must converge for the full integral to converge. So for example, like we have this this section right here. If going from A to C it diverged, but B to C converged, then going from A to B would diverge, because essentially it doesn't matter if, like, you can say going from B to C that equals 2. If going from A to C equals infinity, then infinity plus 2 is just infinity. Like, you have to have everything to converge. So let's do an example for this. Yeah, we're going to do a quick example because we have 15 minutes and one more section to get through. Okay, so if we want to see if this is convergent or divergent, we have the improper integral from 9 to 0 of 1 over x minus 1 to the 1/3. Do we have any discontinuities in here? Just go ahead and put like where we would have a discontinuity, or if one of the bounds is causing an issue. So we would have a discontinuity at 1, right? Because 1 minus 1 would get a 0 in the denominator, so we'd have a discontinuity at 1. So therefore, we'd have to break this up into two integrals, going from 0 to 1, and then from 1 to 9. And then, of course, we can turn this. We can say we're taking the limit. We can say from here as t approaches 1 from the negative, and the limit over here as t approaches 1 from the positive. So what we can do, what I typically find easiest to do, is to go ahead and solve for the indefinite integral first, and then just go ahead and plug and chug at the end. So if we take the indefinite integral of x minus 1 to the negative 1/3, from here we can do a u sub to let u be x minus 1. du is dx, so therefore we get u to the negative 1/3 du, so therefore we get 3/2 u to the 2/3 plus c, 3/2 times x minus 1 to the 2/3 plus c. So now we need to go ahead, look at our two individual integrals. So if we have our limit, so let's go and look at this one first. If we have the limit as t approaches 1 from the negative of, we have 3/2 times t minus 1 to the 2/3 minus 3/2 times 0 minus 1 to the 2/3. We can look and see if we approximate 1, that's essentially going to get us approximately 0 right here for t minus 1. So 0 to the 2/3 is 0. So 0 minus, we have 3/2, we have 0 minus 1, and that's to the 2/3. So if we think about that, we can square it and take the cube root. So negative 1 squared is 1, cube root is 1 times 3/2. So we get minus 3/2. So therefore, that first one is convergent. The second one we have is going from the positive, and we have in that one was going from t to 9. So we have 3/2 times 9 minus 1 to the 2/3 minus 3/2 times t minus 1 to the 2/3. So we have 9 minus 1 is 8 to the 2/3 is going to be 4 times 3/2 is going to be 6. And once again, we can approximate t minus 1. That limit is going to approximately be 0 when we take the limit. So therefore, that whole second term right here is going to be 0. And since both of these limits exist, we can say that this one is convergent to, and you go ahead and add these together, so 6 minus 3/2, I believe that 6, that is going to be 9/2. So yeah, since both those are convergent, the full thing is convergent. Real quickly, I just want to go ahead and mention limit comparison theorems. So this is essentially if we have some function, f of x, which is bigger than another function, g of x, which is bigger than 0. The way it's stated is typically just for like a type 1, but you can use this for any type. So we have, if we have an integral going from some number a to infinity of f of x is, dx is convergent, then that same integral of g of x must also converge. Similarly, if the integral of g of x is divergent, then that same integral of f of x must also be divergent. And this is essentially because if we have two functions, if we have f and we have g, if we know that f is, let's say, 5, that area under f is 5, g would have to be some sort of finite number because it wouldn't make sense for f to be bigger than g and then the area under g is infinity, whereas f is 5. G would have to be less than 5. Similarly, if we knew that g was infinity and f is bigger than g, f can't be a finite number because infinity, it can only be a bigger infinity. So that's why that theorem kind of works. Does anyone have any quick questions before we move on to arc length? All right, let's go ahead and move on to arc length. That's our last section. So just the highlights that you need to know are going to be your arc length formulas. So arc length. If f prime of x is continuous on the interval a to b, then the arc length from a to b is equal to the square root of 1 plus f prime of x squared dx. I don't have really time to get into the proofs behind this. They are in your textbook. And you still have a couple days to go ahead and ask your prof if you want like more info, but like this is just kind of like more so what you need to know for the test. Similarly, if g prime of y is continuous on c to d, and we know that x is equal to g of y, our arc length then would be from c to d of the square root of 1 plus g prime of y squared dy. So I'm going to go ahead and do like an example, and this is actually one that tends to pop up like a not uncommon amount, like this kind of format. So in this example, we are going, so in this example, actually, let me just go ahead. The problem states that we want to find the arc length whenever we have the function y is equal to x cubed over 3 plus 1 over 4x, and we know that x is in between 1 and 2. So our first step that we would need to do for this is we can go ahead and take the derivative of our y. So we can say that dy over dx, we have x cubed over 3 goes down, when we take that derivative, is going to go down to x squared. And then if we take the derivative of 1/4 x to the negative 1, that is going to turn into a minus 1 over 4x to the negative 2, or 1 over 4x squared. So now we can go ahead and plug this into our formula. So we know we're going from 1 to 2. We already have the square root of 1 plus our dy dx squared. So x squared minus 1 over 4x squared, all squared. Our next step would be, let's go ahead and FOIL out that this squared portion. We get x squared minus 1 over 4x squared, all squared, is equal to x to the 4th. We get minus that x and the 1 over x squared will cancel out, so we're just going to get minus 1/4 times 2, so a minus 1/2, plus a 1 over 16 x to the 4th. So now we can go ahead and plug that in back into our integral. So where we get 1 plus x to the 4th minus 1/2 plus 1 over 16 x to the 4th. We can simplify out this 1 and the 1/2. So I was going to say a plus 1/2 right there. So if we look at this section under our radical now, it looks very, very, very similar to what we got up here. The only difference is that this sign right here changed. So what we can do is we can actually say, recombine this to get x squared plus 1 over 4x squared. Because if we FOILed it out, it would be the same thing that we got up here, it's just that negative would then turn into a positive. And that's all squared. That square root and the squared will cancel out. We can just do a basic power rule from there to get us 1/3 x cubed minus 1 over 4x, going from 1 to 2. And then we get 1/3 times 2 cubed minus 1 over 4 times 2 minus 1/3 times 1 cubed minus 1 over 4 times 1. We get 8 over 3 minus 1 over 8 minus 1 over 3 plus 1 over 4. And then we eventually get 7/3 plus 1/8 once we simplify. If we cross multiply, we get 56 over 24 plus 3 over 24 plus 59 over 24. And that will be our final answer. So does anyone have any quick questions over anything that we covered today?
I got pulled away from my computer for a second. Can you just scroll up so I can copy this problem down whenever you get a chance?
Oh yeah. And this will also be uploaded onto YouTube for the next day or two as well. So if there's also anything else that anyone needed to go ahead and wanted to rewatch, you can go ahead and look those up. We also have weekly review videos. Almost every section that we covered today has a weekly review video attached to it. The only section that does not would be 8.1. If there is a certain section that you wanted to see more practice on, you can also look at that as well. Does anyone else have any other questions? All right, so if no one has any questions, I'll go ahead and stop the recording.